Another classical problem when it comes to coding interviews. On one hand, this problem is super simple to understand. You are given two sorted arrays and you have to tell me the median. And on the other hand, this problem is categorized under the hard difficulty. What makes this problem so special? You will soon realize it when you try to solve it. They are expecting that you come up with a solution that works in the logarithmic time. So what do you do about it? I will try to go step by step over each of the possible solutions and what is the problem with it. We will then work towards an efficient solution, and you will be surprised to find out that the most efficient solution to this problem requires the concept of a binary search. And somehow this makes it a little easier to solve. Let's see what we can do about it. Hello friends, welcome back to my channel. First of all, let us quickly make sure that we are understanding the problem statement correctly. In this problem, you have to tell me the median of two sorted arrays. So basically, you are given two sorted arrays like this. And they are sorted in themselves. This array is completely sorted and this array is completely sorted. Both of them are in the ascending order. And you have to tell me the median. Mathematically speaking, what is the median? Median means when you have a series of numbers that is in an ascending order and then you tell me what is the middle number. How do you define a median? For example, if you have an odd count of elements, so let us say I have all of these numbers. I have sorted them in an ascending order right now. If you find them out, these are a total of 7 numbers. So where does the median lie? The median number will be 13. That means it is at 7 plus 1 by 2. This position, this is the fourth position. And what makes it the median? You have 3 numbers on the left and 3 numbers on the right. So this number is somewhere in the middle, correct? Now, what about when you have an even count of elements? Once again, take a look at this particular array. This is already sorted. So if you have to tell me the median, how will you find it? You have a total of 8 elements. Now, there is no central element. But I can say that, okay, these 2 elements are the central element because you have 3 elements to the left and 3 elements to the right. So what is the median? The median will be the summation of both of these numbers divided by 2. When you do that, you will get 80 divided by 2 and you will get 40 as your answer. So this is how you find out the median of odd count of elements and the median of even count of elements. Going back to the problem statement, what do you need to do now? You are given 2 distinct arrays which are sorted. And you have to tell me what will be the median when you combine both of them and then tell me that, okay, this is the median element. Now, all of this seems pretty easy to understand. But what is the hard part about it? The hard part comes when you actually try to solve it. If you think about the most naive way to approach this problem, what will that be? It will be the brute force method. These are the 2 arrays that I am available with, correct? What you can do is, you can simply write down both of these arrays side by side. So I create a new array and you notice that this array is present over here and then this array is present over here. I have combined both of them. So what do you do next? To find the median, there is a condition that you have to sort the array. So what you can do is, you can sort this entire array and then you will get something like this. Once you get this, finding the median becomes very, very simple. You have a total of 11 elements in here, correct? So the median will be 11 plus 1 divided by 2. And that is the 6th element. So you calculate 17 is the 6th element. So this is your median. Why? Because you have 5 elements on the left and you have 5 elements on the right. So 17 is the answer. And yes, this is a perfectly valid solution and it will give you a correct answer every time. But it is not efficient. However, you have now established that how can you find out the median? That what will be the answer when you are given such a problem statement. So what do you do about it? How can you now solve it and how can you optimize it? Because right now, if you think about it, joining both of the arrays won't take up so much time. You just combine them. The main problem happens when you try to sort this array. The fastest you can do is quick sort. And that works in a n log n time complexity. But that is not expected. You waste so much time over there. But if you realize, do you actually need to sort the entire array? What if you just take 2 pointers and then try to find out the position? Can we work our way something like that? So let us look at the 2 pointer method. What are we available over here? We are given these 2 arrays, correct? And you can safely count what is the total number of elements. You say that, okay, both of these arrays have a total of 11 elements, right? Now, you know that if there are 11 elements, what will be the median? Median will be 11 plus 1 divided by 2. That is the 6th element. So somehow you have to get to the 6th element. Notice that you don't have to sort the entire array. You can still take advantage of the fact that both of these arrays are already sorted. So what I'm going to do over here is, I'm going to start 2 pointers at a negative location. Notice that this is not even starting at the first position. But I need to determine that, okay, what will be the first element of my sorted array. So how can you do it? What I'm going to do is, I'm going to take a counter variable that is counting how many elements have I passed. Currently it is 0. Now you have to go to the 6th element, right? You know that once you merge both of these arrays, either you will have a 1 or you will have a 2, correct? And how will you determine which element to get? You are gonna check, okay, which element is smaller. Because 1 is smaller, what I will do is, I will just move this pointer to the next location. So this pointer is now pointing at 1 and this is still pointing at 0. But I have now established that, okay, with one move, I am at this position. So I have determined that, okay, this will be the first element of my sorted array. So the value of this counter changes to 1. It means I have covered one element. Now keep on doing it. You have to determine what will be the next element. So how do you find out the second element? You are going to compare 12 and 2. Out of these, what is smaller? 2 is smaller. So don't do anything. Don't take up any space. Just move this pointer ahead. What I have now done is, I have determined that, okay, I know about 2 elements and these will be the 2 elements. But I have to go up to 6th element. Observe the next element. You have 12 and 13. Out of them, what is smaller? 12 is smaller. So you simply move this pointer one step ahead. And my counter changes to 3. This time you are going to compare 15 and 13. What is smaller? 13 is smaller. So I will move this pointer one step ahead. I have covered 4 elements. Now move ahead. You have 15 and 17. Out of them, what is smaller? 15 is smaller. So I move this pointer one step ahead. And I have covered 5 elements. So up till now, notice, I have determined that in my sorted array, 5th position will be this particular element. I have to now find out the 6th element. To do it, what I'm going to do is, I'm going to compare 26 and 17. Out of them, 17 is smaller. So what I'm going to do is, I'm just going to move this pointer ahead. I have now reached the position 6. Since I moved this pointer, I know that this is the 6th position and this becomes my answer. So what did we just do? We did not sort the entire array. We just moved our pointers according to that, okay, what number is gonna come in my merged array. This is the 6th position and this will be the number. So that is the answer, correct? And if this is not clear to you, let us take a step back. Instead of 26 and 17, what if you had the number 16 over here? What happens now? You are going to compare 16 and 17. Out of them, 16 is smaller. So you are going to move this pointer ahead. And what does this do? The counter again becomes 6. It means that this 16 will become the median. Why? Because now this array has changed. This 17 will be at the next position, right? So you are easily able to determine that, okay, at the 6th position, I am going to find out my median. What if the total number of elements was even? Then instead of finding just this, you are going to find out 6th position and the 7th position and then just divide by 2. So basically you would have got 16 and you would have got 17. You would add them and you divide it by 2. So no matter if your length is even or if your length is odd, you can easily determine that what is the median going to be. Now tell me, what is the space complexity of this method? The space complexity of this method is order of 1 because we are not taking up any extra space. But what about the time complexity? The time complexity will be order of m plus n divided by 2. because you need to traverse at least this much steps to reach the median element, correct? And this eventually translates to order of n. So from the quick sort time complexity, order of n log n, we have now reached a linear time complexity. So at least this is some improvement and advantage over what we had. And I think that if this problem was under medium difficulty, this would have been enough. You have determined that, okay, without taking any extra space in a linear time, I can find out the median. And this is pretty fine. But you are expected to come up with a solution that works in a logarithmic time. And somehow, whenever you see the time complexity that is expected to be logarithmic, you need to partition your array. You need to apply the binary search technique. It is a very, very big hint, because you can only achieve it when you discard half of your problem set. Only then you will be able to narrow down very, very fast, correct? And how do you partition? If you think about the concept of a median once again, as soon as you find a median element, what happens to left and right? On the left, you have an equal number of elements and all of them are smaller. On the right, you also have an equal number of elements and all of them are greater. This is the concept of a partition. And if you have found out the right partition, you have found out the median. Just pause this video over here and let this thought stick in your mind for a while. All the numbers to the left of the median will be smaller and all of the numbers on the right of the partition will be larger. And the quantity, it will also be the same. This is very, very essential that you understand before you can come up with an efficient solution. Basically, what I'm saying is, if you have an array something like this, and you determine that, okay, this is my partition. You now have a left half and you have a right half. All of these numbers will be smaller than the partition and all of these numbers will be larger. This is where the partition lies. And this is how you can separate an array. What is the other important property of a partition? If you create a partition, all of the elements on the left should be smaller than all of the elements on the right. If you think about it, this condition holds true. But for a partition to be a median partition, the number of elements on the left should also be equal to the number of elements on the right. Only then you can make a partition that is a median, right? Over here, you have 11 elements, correct? So if you try to split it into two, in the first half, you will have 6 elements and in the second partition, you will have 5 elements. This is fixed and you must understand it. You cannot have any other partition. So now you have fixed that, okay, in one of the partition, I am gonna have 6 elements and in the other partition, I am gonna have 5 elements. So you are able to rule out some of the partitions very, very easily. You can never have a partition like this because on the left, you have only 2 elements and on the right, you have all of these elements. And that is one thing that you have established. You have established that I will have 6 elements on the left and 5 elements on the right. You can also reverse them. The solution won't change because you have to divide 11 elements in some way or the other, correct? Just for this problem, I am saying that, okay, let there be 6 elements on the left and 5 elements on the right. So how do you make these partitions? The beautiful part is that as soon as you fix a partition in one of your array, the partition of your next array is automatically determined. You are saying over here that, okay, in my first array, I am going to have 2 elements. So how many elements are remaining in your left partition? That is 6 minus 2 and that is 4. You have to compulsorily take 4 elements from your second array. So your partition will come somewhere over here. So what partition did you create? Basically, you created this partition. You now have equal number of elements on the left and equal number of elements on the right. But is this partition valid? No, because all the elements on the left should be smaller than all the elements on the right. But if you notice over here, 30 is greater than 15. So this partition is not valid. So what do you have to do? You have to somehow determine a partition that is valid. So let us say I am taking a partition of only 1 element. So in my second array, where will my partition lie? It will lie at 5 elements. So I am creating this particular partition. Is this valid? Once again, no, because 45 is greater than 12. and all the elements in the left should be smaller than all the elements on the right. What if I take up 4 elements from my first array? Then how many elements do I still have to pick? I have to pick up 2 elements. So my partition becomes something like this. But is this valid? No, because all elements in the left should be smaller than elements on the right. But over here, 26 is greater than 17. So this partition is also not valid. You can also take up all of these 5 elements in the first partition and just this single element in the second partition. On the basis of size, this partition is valid. But is it a median partition? No, because 38 is greater than 13 and this does not justify our criteria. So, will we be able to find our partition? Yes, let us check up one more position. What if I put my partition somewhere over here? I covered 3 elements in this. So, how many am I remaining with? I am remaining with 3 more elements. So, I will have my other partition over here. What does my complete partition look like? This is my left half and this is my right half. Do I now satisfy every criteria? Check it out. In my left quantity, I have 6 elements. In my right quantity, I have 5 elements. So this is a good partition based on the median. Now we need to check, is every element on the left smaller than every element on the right? And if you notice, this condition holds true over here also. So I can safely say that this partition is actually valid and I can now use this to determine my median. How? Because now I know that just all of these 4 numbers, they determine what will the median be. If my total length is odd, I just need to find out the maximum of these numbers. If my total length is even, then I need to find out the average of both of these numbers. And that is how I do not need any other elements. I just need to find out that, okay, where does my partition lie? This is the beautiful part where you have to take advantage of sorting also. Because if you notice, to determine that my partition is valid, I do not need to look at all the elements. I know that my array is sorted. So I know that any element before 15, it is smaller. Any element before 17, it is smaller. After 26, it is greater, and after 30, it is greater. What I want you to do is look at the problem statement from this particular point of view. We are not interested in all of these elements. I am only interested in these 4 values. It means wherever I put a partition, I need to know the L1 value, the R1 value, the L2 value, and the R2 value. To determine the partition, what did we do? You count all of the elements and find out that, okay, the number of elements on left should be this much, the number of elements on the right should be this much. You got one criteria for your partition. Once you have now made these partitions, you notice that these partitions could have been made in any way, right? And the value of L1, L2, R1, R2 will change. But how do you determine that, okay, these are the good values of L1, L2 and R1, R2 such that I will get the median? You have to ensure that all of these values are smaller than this. And to do that, since these arrays are sorted, if L1 is less than equal to R2, it means that all of these values are smaller than this. And if L2 is less than equal to R1, then all of these values are smaller than this. Right? And that is what we wanted. Because all these values are already smaller than this. I have determined that all these values are smaller than both of this. Correct? And all of these values are already smaller than this. And I have determined that these values are smaller than this also. So this entire set is smaller than this. And this entire set is smaller than this. So I can safely say that this is my valid partition. Once again, take a moment and absorb this thought. Why is a partition important? How do you determine what is the length? And how do you ensure that this is a good partition? If all the elements on the left are smaller than all the elements on the right. You know that if you have found out this partition, you have found out the median, correct? But how do you find out this partition? Sure, you can go iteratively one by one from the first array and try to bisect your second array, correct? That is what we were doing. But this tells you your first array is sorted and you are going step by step. What do? You apply the binary search technique to find out the partition. And you will soon notice what makes this problem so much fun to solve. Once again, I have my both of these arrays. And this time, we are going to use our binary search technique to find out this partition. Also, we have determined our two conditions. I want 6 elements on the left and 5 elements on the right. And this condition has to be true for a valid partition. To find out the valid partition, you start from the smaller array. Because if one of your array is huge, then applying binary search on it may take time. And if one of your array is smaller, you can easily find out that partition. So to find out the partition, what do? Low is 0 and high is 5. This is how we do a binary search, correct? To find out the mid, what do? 0 plus 5 divided by 2, and that gives you the second position. It means I will try to apply my partition over here. Since you have taken 2 elements from the first array, you want to have more elements from your second array. How many elements? 6 minus 2, and that gives you a 4. So you will take up 4 elements from your second array. So what does this do? It kind of gives you a partition, right? Now, how do you determine if this partition is valid? Basically, now you have got 4 values. This is L1, this is R1, this is L2, and this is R2. So you will try to verify this. Is L1 less than equal to R2? Is L1 less than equal to R2? Yes, so far so good. Is L2 less than equal to R1? Is L2 less than equal to R1? No. It means this partition is not valid. So what did we just do? We have just eliminated one of our conditions. It simply means that this particular partition wasn't good enough. And what do we do with binary search? We need to move either our high pointer or our low pointer. What we are going to do is, we are going to move our low pointer to this position plus 1. So low pointer now points over here. That is the position 3. To find out the mid element, proceed with your binary search. You do 3 plus 5, and that gives you 8 divided by 2. That is the 4th position. So this time, what we're going to do is, we are going to try to put our partition at 1, 2, 3, 4. We are going to try to put our partition over here. Since we did this, we took 4 elements. We need 2 more elements from the second array. So I put my partition over here. Is this partition valid? Once again, I got L1, R1, L2, and R2. So I check, is L1 less than equal to R2? L1 less than equal to R2? No. This partition is obviously failing. So this is also not valid. Since this time we took too many elements from over here, to apply the binary search, this time let me try to reduce the high pointer. So this gets reduced, and this time my high pointer will actually point at the 4th position. You do 3 plus 4 divided by 2, and you get 3. That means this time I will try to apply my partition at the 3rd position. If I apply it at the 3rd position, how many elements am I remaining with? I am remaining with 3 elements. So in the second array, also find out the partition at 3 elements. So once again, you got your another partition. How do you determine if this partition is valid? You got L1, R1, L2, and R2. Try to validate both of these conditions. Is L1 less than equal to R2? Yes. Is L2 less than equal to R1? Yes. So now you have determined that, okay, this condition holds true and this condition holds true. What does it mean? It means I have found out a valid partition. And how do you find out the median? You just take a maximum of both of these numbers. Why? Because remember, your array was odd length, right? 11. So you want 11 plus 1 by 2. You want the 6th element, correct? You have 3 and 3. So the maximum of both of these numbers will be the actual 6th element. So this is your answer. So notice, what did we just do? We did not do multiple iterations. We just did the binary search technique to determine where my partition will lie. And then I just need to validate, is my partition valid or not? So I know that this is not pretty straightforward, but if you understand how does a binary search work and how are we partitioning, then this problem becomes fairly super simple to solve. And remember, it is asked in a lot of coding interviews. Let us quickly do a dry run of the code and see how it works in action. It will be actually best if you try to implement it on your own. But what I'm going to do is, I will go over the code very, very quickly. So first of all, what we do is, we try to determine what is the smaller array. just so that I can find out my result faster. I have found out that, okay, one of them is my smaller array, and then I assign the low and high pointers accordingly, correct? I also find out the total length. This total length is gonna help me find out, okay, if I have picked up X elements from my first array, how many elements do I need to pick up from the second array? And also, this total length helps me determine if my resulting array will be even or odd. I have got my low and high values. Next, what I do is, I run a while loop. In this while loop, I try to partition the first array, that is the array X. I do a low plus high divided by 2. So I have 0 here, I have 5 here. So 0 plus 5 divided by 2, I get a 2. It means I am trying to partition at the second place. As soon as I find this partition, I need to tell, okay, where can I partition Y? To do this, I use my total length and subtract the value. So I get partition Y equals to 4. Then I need to compute what is the value of L1, L2, R1 and R2. And I am doing some sanity checks over here. Because what could happen is your partition could land somewhere at the end also. So how do you account for over here? There is no value. So in those cases, we take a max value. If your partition lands at the 0th position, then what do you do? Then I take an integer.min value. These are just sentinel values which help me to reduce index out of bound exceptions. I have got my 4 values, L1, R1 and L2, R2. I have got my 2 partitions. It is now time to check if my condition holds true. If L1 is less than equal to R2 and L2 is less than equal to R1. If this is true, I have found out my partition. So what do? If the length is even, then I take an average of both of these numbers and divide it by 2. If the length is odd, I take a maximum of L1 and L2. That is what we were actually doing, right? If this partition is not valid, what do? If L1 is greater than R2, I move my high pointer. Otherwise, I move my low pointer. And once you do it, this loop completes, and at the very end, you will find out your median somewhere in here. In some time, you will eventually land at the correct partition. So your answer comes out over somewhere over here. And notice, we are not taking up any extra space, and this is working in a logarithmic time complexity. And that is what we needed. I hope going over this problem step by step actually helped you to clear out all of your doubts. I know that this is not actually very straightforward, and you cannot come up with this kind of a solution. But noticing these patterns and trying to understand what would a partition mean, how can you apply the binary search technique? A very good hint is that, okay, you have to use the logarithmic time complexity. That can only happen if you use a divide and conquer strategy. And that is where the binary search shows up. So while going through the video, did you face any problems? Or do you have any other method in mind by which you can solve this problem in an even easier way? Just tell me everything in the comment section below and I would be happy to discuss all of them with you. As a reminder, if you found this video helpful, please do consider subscribing to my channel and share this video with your friends. This really keeps me motivated and I can make more such videos. Also, a huge shout out to all of the members who support my channel. You guys are the real rock stars. And remember, now you can schedule a one-to-one session with me and we can discuss about almost anything. All of these links are available in the description below, and I have got some super helpful resources for you. There's a LeetCode navigator, there's a smart interview grind, which can help you with all of your interview needs. So check it out. As for my next video, stay tuned. Until then, see ya.